Alright, when we first start out, we're going to take a look at antiderivatives, and the antiderivative we're going to take a look is antiderivative to the x dx. And since I don't know what to do on this one, what I'm going to do is I'm going to let u equal to the x. And I just, from the previous, excuse me, let me get rid of that. From the previous video, I know that when I take the derivative of 2 to the x, I'm going to get the ln of 2 times 2 to the x. Well, that means du is equal to the natural log of 2 times 2 to the x dx, and I have 2 dx, but I don't have the natural log of 2, so I'm going to write this as 1 over the natural log of 2 du is equal to 2 to the x dx. And I'm going to replace this with that. And so now I have 1 over the ln of 2 du. Well, what's the antiderivative of that? Well, that's going to be 1 over the ln of 2 times u plus c. Well, what's u? U is 2 to the x plus c. So now my shortcut is, let's say I'm taking the antiderivative of 3 to the x dx. Well, that's going to be 1 over the ln of 3 times 3 to the x plus c. And I can go through the same process to get that, but I should start seeing a pattern if I have 5 to the x dx. My antiderivative is 1 over the ln of 5 times 5 to the x plus c. Alright, another problem I have is now, what if I have this 2 to the 2x dx? Well, I know what it is if it's to a single power, but now I've got this kind of complicated thing. So what I'm going to do is I'm going to let u equal 2x du dx is equal 2, and I'm going to get du is equal to 2 dx. I don't have a 2 dx, so I'm going to have to write 1/2 du is equal to dx, and so I'm going to have 1/2 times 2 to the u du. Well, I'm going to have 1/2 times 1 over the ln of 2 times 2 to the u. Well, what is 2 to the u? U is 2 to the 2x plus c. So I can write that up a little bit nicer. I can write 1 over 2 times the ln of 2 times 2 to the 2x plus c. So that's my antiderivative, and I can generalize that even further. I can clear that, and I can say, alright, if I have something that looks like this, a to the g of x, and I have the derivative, the chain inside the integral dx. Well, that answer is going to be 1 over the ln of a times a to the gx power plus c. And that's my general formula. Okay. The next thing are some interest problems. Clear. And one is the compound interest problem. And you're told that a equals, a is equal to, or the amount that you get is your principal times 1 plus R, which is your rate, over N times your number of compounds per year raised to the NT power, where T is number of years. And if you look at your notes, all those values are listed. That's your compound interest formula. And then you have another formula, which is A equals, sometimes it's called PERT, your principal times e to the RT power. And in this case, every moment that's going by, you're compounding. And we're going to take a look at a couple of problems. First of all, number 11. It gives you a principal of $2,500. So A equals 2,500 times 1 plus, and it's for 5 years, and you're going to compound it annually at a rate of 7%. So it's going to be 0.07. Annually would be once, raised to the 1 times 5, because it's 5 years. And then the next one, it's compounded quarterly. So now I have 2,500 times 1 plus 0.07 divided by 4 raised to the 4 times 5. And then the last one is that it's continuously, so I'll put the separation symbol here. And A equals 2,500 times E to the RT, which is 0.07 times 5. Alright, which is the same as A equals 2,500 times e to the 0.35 power. Alright, so let's see what each of these. This one's going to be, let me just simplify this up a little bit. 2,500 times 1.01, or excuse me, 1.07 raised to the 5th power. And I'll go to my calculator to figure that out. Uh, 2,500 times 1.07 raised, what did we say it was? The 5th power. And we get $3,506.38. $3,506.38. I hope that was correct. Yep, it looks good. Alright, the next one is 2,500, and I'll actually use the parentheses here. 1 plus 0.07 divided by 4 raised to the 20th power. And I'll get 3,536.95. 3536.95. $36.95. Alright, so I made a little bit more money compared to this one, a little bit more than $30. And so now let's take a look and compare it to this one. And it's going to be 2,500 times e to the 0.35 power. And I make a little bit more, $3,547.67. So that gives you the most because that's continuously. So let's clear the screen and take a look at our last problem, number 12, and says, alright, what if we're compounding monthly? How much time would it be required for the investment to double? Well, so if P is my investment, I want to know when it's going to be 2P, twice as much. And I'm compounding monthly at a rate of 12%. So I'm going to take 0.12, monthly is 12, and I'll have 12 compounds times how long, I don't know. I'm going to let that be my variable t. I'm first going to divide both sides by p, and I'm going to get t equals 12 divided by, or 0.12 divided by 12, I think is 0.01. So this is going to be 1.01 raised to the 12t power. Well, how do we get access to that variable? We take the natural log. So I have the natural log of 2 equals 12t times the natural log of 1.01. So now I have the natural log of 2 divided by the natural log of 1.01 is equal to 12t. And so now I have the natural log of 2 divided by the natural log of 1.01 divided by 12 equals t. Now, there is something called the rule of 72 that business people use a lot that says if you take your time times your rate, it should approximately get to 72. That's kind of a linear problem. It's a little bit off, but it's pretty close. So if my time, I would take 72 and divide it by my 12%, I should get somewhere approximately close to 6. So I'm going to bring my calculator up again. And I'm going to take the ln of 2. Oops. Let's exit this and go to here. There we go. Alright, now I'm on the right page. I got the ln of 2 divided by the ln of 1.01 divided by, oops, I'm going to delete that. I'm going to press enter, and then I'm going to divide that by 12. And I get 5.81. So 5.81 years is pretty close to those 6 years.